This is lesson 5.8, applications. So here we'll have some story problems finally, as we've been doing a lot of things with properties and not really applying it to anything in the real world. There'll be a couple of problems like that here. For the warm-up, you should be able to do all of these problems on your own. I'll do D with you, and then the rest of them I think you should be able to do on your own. But I'll do D just in case you need the refresher and support. Okay, so here I have for D, I have log x minus 3 log 2 equals 2. I think I'll use the quotient property to make this division problem, but before that, this second term, I got to get the 3 up there. So this is going to be log x minus, and then this is log 2 to the third equals 2. 2 to the third is 8. So this is the same thing as log x minus log 8 equals 2. Now I can write it as a quotient. So it'll be log x and then, oops, I didn't really want to do it like that. Log x over 8 equals 2, like that. Now, this one doesn't have a base shown, but there is a base. The base is 10. So if I do, put a little 10 there, 10 squared equals, I'm using the definition of logarithms here, 10, and then over squared equals, and then the argument, x over 8, like that. 10 squared is 100. Multiply both sides by 8, x equals 800. Can you plug this into your calculator and see if it's correct? Yes. Do log 800 minus 3 log 2, and you'll see that it equals 2. So that's a good way to check and make sure when you do your test that you are checking your answers like that. All right, you should be able to go ahead and do A, B, and C. All right, let's take a look at these. So for A, you can use a product property to get log base 6, 10x equals 3, change it to an exponential here, and then you get 216 equals 10x, divide by 10, x equals 21.6. For B, you're going to use the quotient property. So you get log base 7, x over 6 equals 2. Use the definition of logarithms to get 7 squared equals x over 6, and then to get 6, or the x by itself, multiply both sides by 6, and you get x equals 249. C is really crazy. So if you felt kind of like I have no idea how to do C, I have 2 ways, one in orange and one in purple. The purple way down below is definitely the easiest way, and it wasn't the way I went with initially because I was thinking, oh, I want to use the power property and the product property, and that's what I did in orange. So what I did in orange is I brought the 4 and the 3 up, to the top there. So then I had x to the 4th. That should have been a plus sign right there. And then log x to the 3rd. And then I use the product property. And so I get log to the 4th times x to the, x to the 4th times x to the 3rd, which is x to the 7th. Then I decided to change this to now I could have brought the 7 down here and then divided by 7, both sides by 7, but I didn't. So then I have 10 to the 1765 equals x to the 7th. And then I would raise both sides to the 7th using the power property. But regardless of how you do that problem, you end up getting with an overflow answer. Like your calculator cannot handle how large that answer is, and so it'll say error overflow. Now, a way easier way to do this problem is what I did down here. If I would have recognized at the beginning of the problem that these are like terms, log x is a like term that both of them have, and I can just add them together and say that's 7 log x. Then I can get log x by itself by dividing both sides by 7. And then I decide, okay, so then I get log x equals 252. This is a base 10 here, so I can change this to 10 to the 252.143 equals x. You're going to get the overflow there as well. D we did together, so we don't have to talk about D. So one of the last things we're going to talk about with the log chapter here is this other method you can use for more complicated problems where you can put a logarithm the log thing in front of both sides of an equation. Now, this typically happens when you have an exponential equation and both sides have exponents, and you're trying to solve this thing, but like in this case, you have a to the x equals a to the x equals b to the y. They both have exponents. You can't use the definition of logarithms on something like that because definition of logarithms, there's only an exponent on one of the sides per the definition. So this doesn't work anymore. And so this is something we can use to solve these problems. I am going to do a couple that you actually could use a definition of logarithms for, but we'll start there and then we'll get on to some of the more complicated problems after that. All right, so it says here log x times 5 to the x times 5 to the third equals 625 for number 1 here. Okay, so they have the same base, so I can use the product property of exponents and say this is x plus 3, just to kind of condense that. All right. Now this one you could use same base, because 625 is actually 5 to the fourth, and we could solve it that way. But we're not going to do it that way because it wants us to solve by putting a log on both sides. So I'm going to put a log in front of this side and a log in front of this side, like that. And now I can use the power property of logs and bring this x plus 3 down to the front. When you do that, you may want to put parentheses around it because that whole thing is multiplied to log 5. Now I want to get this, let's get the x plus 3 by itself. You could distribute log 5 in here like that, but that just gets really sloppy with decimals quickly. So if you can avoid that, evaluating the log until the very end, that's better. So I'm going to divide by log 5. I get x plus 3 equals, and then funny enough, log 625 divided by log 5 is equal to 4. Then I can subtract 3. X equals 1. All right, should you put this in your calculator? Yes, you should. And actually, if you do that and you think about it, this would be 5 to the first times 5 to the third, which is 5 to the fourth. 5 to the fourth, 5 times 5 is 25, times 5 is 125, times 5 again is 625, so that works. All right, let's try another one. Now again, you don't have to use putting a log on both sides for a problem like this. This problem, if I saw this, I'd probably use definition of logarithms, and I would say, start with the word log, put the base there, 15 equals x, and I would just type that into my calculator and I would be done. But we're learning this other method, so that's why we're not doing it that way. All right, so I will put a log in front of both sides because this is another strategy to solve, like this. And I'll bring the x to the front using the power property of logs. And then I will divide by log 4 to get x by itself. X equals log 15 divided by log 4 is going to be 1.953. Notice when you had, especially if you're a TI-83 person, you might notice that is the same thing as this. If you use the change of base property, those two things are the same thing. So it all kind of works out well. Okay, now let's do some ones where you put a log in front of both sides, but they're not so easy. Now, these problems here, you would not be able to use definition of logarithms to do it. I can't do the thing that I just did on that last problem where I change one side into a log and use that because I have two sides of the equation that have exponents. So I put a log in front of both sides. Then I use the power property, which you always kind of do that. And so I'm going to have x plus 3 again. I'll put it in parentheses. Log 6 equals x log 5. Dog is snoring. Okay. At this point, there's a couple things you could do. You could distribute the log 6 to the x and the 3, but I think it's better to keep the log thing together as long, to not change them to decimals as long as you can. So I'm going to get the log 6 over to the other side, which you do that with division. So I just have x plus 3 here. And then here, now I'm going to find this decimal. Log 5 divided by log 6 is 0.898. And then I have that x there. All right. Now remember, x is like 1x. So I'm going to get the x's over to one side, and I'll subtract this 1x over here, just because I have a 3 on the left side, and a little faster if I just leave the 3 over there. So I have that, and then 0.898 minus 1 is 0.102. There's an x, and it's negative. And then I'm going to divide both sides by point, I'll have to do this kind of over here. Divide by both sides by negative 0.102. Not negative 0.102. Divide this negative 0.102, like that. And I get x equals, and if you do that in your calculator, you get negative 29.482. That's the answer. Can you plug that back into your calculator for x? Yes, you can. It'll be pretty close to the, to perfect, but we did do some rounding there, so it won't be perfect. Okay, now problem like 4, notice there's an x and there's a y in this. Typically, if you have one equation with both x and y, you're not going to be able to solve it. You need two equations if you have two variables. But in this case, it's going to work out. So when I look at this, I don't know if you're looking at this and saying, same base. I can use a property of exponents here to solve this. And the property is the quotient property. It's this one, a to the m over a to the n equals a to the m minus n. You can subtract the exponents. If I subtract the exponents, I get 11, and then 6x minus 2x is 4x. And then this side is 56xy. Now we said we were going to put a log in front of both sides. That's the method we're using here. So I'm going to do that next. I'm going to bring the exponents down to the front. 4x log 11 equals, and then here I have xy log 56. If I decide to get rid of the x's here, there's x's on both sides. So if I do that, if I divide both sides by x, okay, then these x's cancel out. These x's cancel out. And then this is where that magic happens, where my x's just were totally eliminated. So now what I have, and again, I'll have to write this down here, 4 log 11. Remember, those are all numbers there. And then on the right side, I have a variable, y log 56. And if I want to get y by itself, I would divide by log 56. And in my calculator, I could type in log 11 n parenthesis divided by log 56. And I would get y equals, and it equals 2.383. All right, that was kind of a mess in terms of all those things there. So I'm going to do what I can here to fit everything else in here. All right, let's do this next problem here. Example E. It says solve for x. Y equals 10,000 times 0.8 to the x when y is 300. All right, so I'm going to put 300 in for y. Like this. This could be a problem where it's like you bought I don't know, something for $10,000. Let's say a car, and it depreciates in value like 20% a year, right? So then your multiplier, your common ratio, would be 1 minus 0.2, which is 0.8. And when is it going to be worth $300? That'd be your end value. It's kind of one of those problems. So and then how long would it take for it to be worth $300? So that is really the setup here. I'm going to divide both sides by 10,000. You cannot do 10,000 times 0.8. That does not work. I get 0.03 equals 0.8 to the x. Now, you could do a log in front of both sides, but we don't need to do that here. We know how to do this with definition of logarithms. I'm going to write the word log, and then the base thing, 0.8, 0.03 equals x. If you have a TI-83, you need to use change of base property. Otherwise, you can just type that into your calculator, doing the math, and then up 2 or 3, depending on your calculator. You get x equals 15.717. Okay. Next problem, same thing. It says y equals 500 times 1.03 to the x when y is 2000, okay? Then you're supposed to find out x. So x is usually like the time. So this problem is kind of like, oh, I put $500 in my bank account. When will it be worth 2,000, right? If my interest rate is 3%, because if your interest rate was 3%, it'd be b equals 1 plus r, and you put a 0.03 there, and that's what you'd have. You should be able to go ahead and solve that one. You should get 46.900 if you do that. So if this were a problem, if you had 3% interest rate and you started with $500, when would it be worth $2,000? It would take 46.9 years. Whew, it's a long time. 3% is not a lot. If you had a stock market thing, you'd want it to perform a little better than that. All right, last problem. Now here it's actually giving us the story problem, so we're going to have to set it up. It says an initial deposit of $500 is invested at 8.5% interest. That's way better than what we had before. Compounded annually, you don't need to worry about that. We haven't talked about compounding this since we skipped chapter 1. How long will it take until the balance grows to $800? So we're not even doubling our money here. This shouldn't take 46 years like the last problem. I start by writing standard form of an exponential. My start value 500 is A. What I want when we get done is Y, 800. And then B, remember B equals 1 plus R. B equals 1 plus, and it's 0.085. This is going up. If it's an interest rate, it's going to be making your money grow. So I will plug these in. 800 equals 500 times 1.085 to the x. Can I multiply 500 times 1.085? No, I cannot. You cannot do that. Don't be that kid, because there are these kids that do that, and when I'm grading tests, it just makes me kind of sad, because I feel like I've mentioned it many times. I'm going to get the 1.085 to the x by itself by dividing by 500. I get 1.6 equals 1.085 to the x. I'm going to change this to a logarithm. Now, today we learned you can put a log on both sides and solve this. You can absolutely do that. But I do tend to think that the definition of logarithms is way faster. So I write the word log, and then I write the base, 1.085, and then 1.6 equals x. Type this into my calculator, and I find out x equals 5.761, which, if you're going to tell somebody, hey, when's your money going to be worth 800? Approximately, 5.8 years, you could figure out 5.8. 0.8 is like, I don't know, almost 10 months or something like that, right? 5 years, 10 months, almost 6 years, Would be an answer, good answer there. So this is it for this chapter, and you should be able to go and do your practice.